No. All right, we're going to take a look at solving basic trig equations using what we learned in algebra, combining that with what we learned in about trigonometric functions. So solving basic trig functions involving sine and cosine, and then we'll look at some with tangent, cotangent, secant, and cosecant. And then looking at them when we have a squared function like cosine squared or sine squared, how we can deal with that. So let's take a look at some where we're going. So if I have an equation like this, 2 cosine of x minus 1 equals 0, and we can solve for cosine of x. Okay. Cosine of x in this case is going to be equal to 1/2, right? Just like we would do with algebra, add 1 to the other side, divide by 2, and now you've got cosine of x is equal to 1/2. Well, now we have to determine, well, where is cosine equal to 1/2? And that's where we can use our unit circles if we need to help us. And on the back of your sheet here. Hopefully you have some of this memorized, but if you were to look at your unit circle and say, well, where is my x value equal to 1/2? So my x value is going to be equal to 1/2. Here is x equal to 1/2. Up here at pi, this is pi over 3. So it's 1/2 square root of 3 over 2. And down here at 5 pi over 3 at 1/2 negative square root of 3 over 2. So the two places that happens on the unit circle is going to be where my x value is equal to 1/2 at pi over 3 and 5 pi over 3. So I've got two answers on the unit circle. Now remember that this function is periodic, so we actually have an infinite number of answers for this question, and we'll look at how to answer it if there's an infinite number of answers. But on the unit circle, these are going to be my two places where, okay. So they're both answers, right? So we've got to be careful because in algebra, when we solve something, usually there's only, well, one answer for a linear equation, two answers for a squared equation, quadratic equation, three answers for a cubic function. Well, with trigonometric functions, we're going to have an infinite number of answers. And on the unit circle, we have two different answers, right? So keep those unit circles. What's up? You said it's the wrong date or something?
Yeah, it's like no add.
All right. Okay. I'll fix that as soon as I'm done here, okay? So it'll take me a couple minutes to fix it. All right, so just like in algebra, we want to collect like terms. We can do the same thing in with trigonometric functions. So begin by rewriting the equation so that sine x is isolated on one side of the equation. So just like we would try to solve for x or y or z or whatever it might be in an algebra expression, okay, we are going to do the same thing with trigonometric functions. So now I'm going to put this negative sign, I'm going to add it to both sides. So now I have plus sign on this side and 0 on this side. And now let's move the square root of 2. We'll subtract it from this side and subtract it from this side. So I now have sine plus sine is equal to negative square root of 2. And sine plus sine is 2 sine of x. Now I can divide through by 2. So just like we kind of did with algebra, but now we're kind of doing with trigonometric function. So now I have sine of x is equal to negative square root of 2. Now, if I wanted to look on the unit circle, where is this equal to negative square root of 2? Down here in quadrant 3 at 3 pi over 4. Down here in quadrant 4 at 7 pi over 4. I've got negative square root of 2 over 2, negative square root of 2 over 2. And here I've got positive square root of 2 over 2, negative square root of 2 over 2. So my two places where y is equal to negative square root of 2 over 2, 3 pi over 4 and 7 pi over 4. So now how, on the next slide, I'm going to show you how to write it when I want to express that as an infinite number of answers. So my general solution for sine of x is equal to negative square root of 2 over 2. First, we found the solutions in the interval 0 to 2 pi. So when you see that expression in the interval 0 to 2 pi, that means on the unit circle, right? So between 0 and 2 pi, where is it on the unit circle? Well, we found that the solutions were, I wrote 3 pi over 4. It's 5 pi over 4. I'm not awake yet. Sorry about that. 5 pi over 4 and 7 pi over 4. So I got 1 out of 2, right? Now, those are the two solutions on the unit circle in the interval 0 to 2 pi. But now, we said that sine of x has a period of 2 pi. So every time we go around the unit circle, it repeats itself. So we're going to add multiples of 2 pi to each solution to get the general form. Now, n, we're going to use as a representation of any number of integers, positive or negative. So what is this going to look like? So for the first answer, I said was 5 pi over 4. I incorrectly said 3 pi over 4 first, but it's 5 pi over 4. And now I'm going to add any number of 2 pi to that, negative or positive. And that just means I can go around the circle n times and I'm still at the same spot. So I can do, that's how we express an infinite number of answers. And I can do the same thing with 7 pi over 4 plus any n number of 2 pi. So it means that when I have my unit circle, and here is 5 pi over 4, and here's 7 pi over 4, I can go around the circle as many times as I want. I'm still back there. Same thing with 7 pi over 4. I can go around the circle as many times as I want, and I'm still back to where I am. So that's plus n number of 2 pi. And so that was, let me write this as 7 pi over 4 plus any number of 2 pi. And here I've got 5 pi over 4 plus any number of turns around the circle, positive or negative. So that's how we write an infinite number of solutions. Okay, we're not going to, yes.
So the first step, find all the solutions, is that just on the graph?
Yeah, so it says find the solutions between 0 and 2 pi. So these were my two answers here. And now I can add any number of 2 pi's to either one of those. And I'm still back to where I started. So now I could do this on a graph on a calculator, but it's a little bit tricky to do it that way. Did I see a yellow slip? Oh, blue slip. Okay. Let's get to it. All right. So keep this slide handy because you're going to need it to remember how to do that on some of the problems. All right. So if we're going to graph this on a calculator, it says, and we're not going to do too much of this, so don't worry about this, but I wanted to show you. It says list all solutions over the stated domain of the solution set. So on the unit circle is between 0 and 2 pi, but a graph goes infinite in both directions, right? So if I wanted to graph sine of x, it's going to look like this, okay? And it has an infinite number of iterations, right? And if I wanted to graph where is this equal to negative 2, negative square root of 2 over 2, and I did that on my calculator with the blue line, you'll see I have an infinite number of intersection points. One happens here at 5 pi over 4. One happens here at 7 pi over 4. And if I add 2 pi to that, we'll put it right here, put it right here. If I subtract 2 pi from this, it'll put me right here. It'll put me right here. It'll put me right here. So those are all the intersection points. Okay. So for my 4 basic functions of sine, cosine, and their reciprocal secant and cosecant, remember that the period is 2 pi. Now we have to remember that with tangent and cotangent, the period is only pi. It repeats itself in quadrants 1 and 3. Okay, so it just goes halfway around the unit circle before it repeats. So our general answer is going to be of this form. So for tangent and cotangent, it's some angle theta plus n iterations of pi. So sine, cosine, secant, and cosecant is theta plus n iterations of 2 pi, because the period of secant, cosecant, sine, and cosine is 2 pi. So we have to go all the way around the circle. With tangent and cotangent, if I have an answer here, I'm also going to have an answer here. And so that's just 1 pi around the circle, halfway around the circle. We'll take a look at some examples. So hopefully it starts making a little bit more sense. So solve this. Well, let's solve for tangent of x. So let's try to isolate tangent squared. Okay. So this is going to tell me that tangent squared is equal to 1/3. So that tells me now I have to take into consideration when I take the square root, both positive and negative square root of 3. 1 over the square root of 3. All right, says because tangent has a period of pi, we can find all the solutions in the interval 0 to pi. So the top half of the unit circle, because it's going to just repeat itself with a period of pi. So if I look at this and I look at down here. where is tangent of x equal to 1 over the square root of 3? Remember, I have to divide y divided by x. So on my unit circle here at pi over 6, I've got square root of 3 over 2 1/2. So y over x, tangent of theta, is equal to, or I can say tangent of pi over 6, because that's my angle, is equal to 1/2 divided by square root of 3 over 2. The halves cancel out, and I'm left with 1 over square root of 3. So it happens at pi over 6. Now, I said that since our period is pi, we're going to have an answer down here as well. So my general form is simply, okay. Oh, I forgot. The tangent equals negative pi over, negative 1 over square root of 3 at 5 pi over 6. Because I have negative square root of 3 over 2 1/2. So my tangent of 5 pi over 6 equals negative 1 over square root of 3. So I've got two answers between 0 and pi. And now that means I'm going to have an answer down here as well. And I'm going to have an infinite number of answers. So I just need to add pi n number of times to each of those answers for the general solution. So again, let me refresh this. We figured out that tangent of x is equal to either 1 over the square root of 3 or negative 1 over the square root of 3. That happens at pi over 6, because tangent of pi over 6 is 1 over the square root of 3. You could use your cheat sheet from last chapter to look up tangent of pi over 6, right? If you need help with that. Tangent of negative 1 over square root of 3 is equal, tangent of 5 pi over 6 is equal to negative 1 over the square root of 3 at 5 pi over 6. So those are my two angles. And then I need to add n number of pi to each one of those for my infinite number of solutions. Yes.
Can you explain how you got like the 1/3 and pi over 6?
Yeah. Let me do it where it's a little bit clearer to see.
They're not on like units.
Well, it is, but you have to do a little calculation. So what I would suggest is taking a unit circle and writing down all the tangents and cotangents of each of these angles too. So here at pi over 6 on my unit circle, I'm at square root of 3 over 2 1/2. So tangent of pi over 6 is equal to y divided by x. In this case, my y is 1/2 divided by square root of 3 over 2. The 2 1/2s cancel out, and I'm left with 1 over the square root of 3. So tangent of x equals 1 over the square root of 3 happens at x equals pi over 6.
Let's say if we got like 2/3, like something that's not.
Well, all of the ones that we're going to have are going to be on the unit circle.
Yeah.
And if they're not, then you can just use your calculator probably. And then we have to add pi n number of times, because if there's an answer here, there's going to be an answer here, here, and here, and here, and infinite number of times. All right, I'm going to jump over on this screen over here to numbers 1 through 4. Tab 5, and I gotta fix the 5.3 here. Oh, looks like it's out of order again. I gotta scroll down. So let's make this a little bigger. So it says, find all solutions for the equation 2 sine of theta plus square root of 2 is equal to 0. We had one similar to this earlier. I can subtract the square root of 2. I can divide by 2, and I've got sine of theta is equal to negative square root of 2 over 2. This happens down here at 5 pi over 4 and 7 pi over 4. And the general solution, I have to add 2 pi n number of times to that. All right, cosine of theta is equal to 1. That only happens at one place, right here, at theta equals 0. So at 0, at 2 pi, at 4 pi, we're just going to add 2 pi n number of times.
Could you
So
go
that
a little longer?
Yes.
Thank you.
All right, you're welcome. All right, let's take a look at 3 and 4. Find all the solutions for the equation over the interval 0 to 2 pi. So this one, we don't have to find all of them. We just have to find the ones on the unit circle. So where cotangent is equal to 0. Now remember, cotangent is cosine divided by sine. So I could graph this on a calculator if I wanted to, but that's a lot of extra work that I don't think you need to do. I could just say, well, if cotangent is equal to 0, well, then where is cosine equal to 0? That's where cotangent is going to be equal to 0. That happens at 2 places. My x value is 0 here at pi over 2, and down here at 3 pi over 2.
Can you zoom in just a little bit?
Plenty of seats up here.
Perfect.
I didn't even read the directions myself. It said use or. I used a comma. So didn't even read my own directions. I think on WebAssign it wants you to separate them with a comma.
You want a comma on WebAssign?
I think it says that, yes. Usually.
WebAssign, half the problems are like not in square roots. They're like super common.
Oh, we'll get there. All right, here I've got square root of 3, tangent of x equals -1. All right, plus 1 equals 0, so square root of 3 tangent x is equal to -1. Divided by square root of 3. And tangent of x is equal to, or tangent of theta if you want to, is equal to -1 over the square root of 3. Where does that happen? That happens here at 5 pi over 6. And halfway around the circle at 11 pi over 6. Because I've got negative square root of 3 over 2, 1/2. So 1/2 divided by negative square root of 3 over 2 is equal to -1 over square root of 3. So the two places it happens are here. So tangent's always going to have an answer across the circle. Tangent and cotangent always going to have an answer across the circle.
I have a question on 1 and 2.
Okay.
When do you put n to pi and when?
Oh, good question. So if it says find all solutions, or if it says find the general solution for the equation, it's going to want it in this form with the plus n pi or plus 2n pi. If it says over the interval or in the interval 0 to 2 pi, then you don't need to do it. It's just asking for those answers, okay? Good question.
Also, what does the 2 represent in the n and the 2 in the pi? Like why is
So that's because for sine, cosine, secant, and cosecant, the period is 2 pi. So it repeats itself after we go all the way around the circle 2 pi times. And for 7 pi over 4, we have to go all the way around the circle until we repeat it. For tangent and cotangent, well, this one's kind of hard to see, but for cotangent and tangent, it's always halfway across the circle. So it's only pi. So for this one, there's always an answer halfway across the circle. So the period is just pi for that. All right, good questions. All right. Now, when we're doing these, we have to be a little bit careful. So let's try, because we have to make sure we don't divide by 0 or do weird things. So let's solve one like this, where I've got really two answers here, because I've got either sine of x is equal to 0 or sine x plus 1 is equal to 0. So I don't need to distribute that across. I don't need to do any extra multiplication or anything. But I just want to look at each one individually, just like we would with a polynomial if we had something like that. So I've got two separate factors. Set each one equal to 0 and solve for x. So for the first one, that's pretty easy. Sine of x is equal to 0. Here at 1, 0, and here at -1, 0. So at 0 and pi. But don't forget that we have to add 2 pi to each one. So 0 plus 2 pi, this was it's got a little bit of a trick to it here. 0 plus, I have to have 0 plus n2 pi and pi plus n2 pi. But since it's right across the circle from it, that really is the same thing as 0 plus n times pi. I don't need both answers, because 0 plus n pi is just going to give me the answer. It's just going to give me across the circle. So that's kind of a tricky answer. So if the answer is right across the circle from it, the only time that's going to happen is if you have it, straight across. So All good? All right, thanks. All right, and on the other side, well, I can set sine equal to -1. That only happens at one place, and that's down here at 0, -1. And that's 3 pi over 2. Oops. 3 pi over 2. And now I have to go all the way around the circle, come back to that. So 3 pi over 2 plus any number of 2 pi after that. So that's kind of two separate problems. And we have, so if I were to plug in any one of these three answers, it would solve the problem. All right, so there's a couple things we have to remember when we're doing these. Collect all the terms on one side of the equation. Try to separate the functions by factoring or by using the identities that we learned to make them all one type of the same function. So you want everything to be in terms of sine or everything to be in terms of cosine. But you have to check your solutions because when we're doing things, we can introduce extraneous solutions. You might remember that from algebra, where things look like answers, but when you actually plug them back in, they're not. And that's because if we're dividing by sine and cosine and things like that, we actually might be dividing by 0 without even knowing it. And by doing so, we might introduce an extraneous solution. So we have to check. All right, so here's one that looks a little bit ugly. So I want to solve cotangent of x times cosine squared of x equals 2 cotangent of x. Well, I think the first thing I want to do is to combine all the terms on one side of the equation. So I'm going to take the 2 cotangent of x and subtract it from the left side here. And I want to set that equal to 0 then, because I moved everything to the left side of the equation. So now how do I solve this? Well, I can factor out now a cotangent x from both sides of, or from both terms. So I factor out a cotangent of x, and I'm left with cosine squared x minus 2. And now I have two factors. They're different trig functions, but that's okay, because I can solve each one of these factors individually for 0. So let's solve for cotangent of x equals 0. And let's solve for cosine squared x minus 2 is equal to 0. So let's try the first one. That one's pretty easy. Cotangent is going to be 0, where cosine is 0. That's up here at pi over 2, and down here at 3 pi over 2, or pi over 2 plus n number of pi's. Cosine squared, this is a little tricky, right? Cosine squared is equal to 2, which says that, well, cosine of x is positive or negative square root of 2. Now you can look all day and all night, and you're not going to find a place on the unit circle where cosine is greater than 1. So this yields no solution on that side. So we only have one answer then. And that's pi over 2 plus n number of pi.
So if it's greater than one, it's not.
There is no solution because sine and cosine, the range is between -1 and +1. Yeah. All right. Take a look at another example here. Now let's just find it on the interval 0 to 2 pi. Let's solve sine of x minus 9 is equal to cosine of x minus 9. Well, the first step is pretty easy. I just kind of do them all at once here. First step's pretty easy. Just add 9 to both sides. Now, if I knew that sine of cosine was equal to, or sine was equal to cosine of pi over 4 and 5 pi over 4, I could just jump down to this step down here, right? Yeah, otherwise I might have to do a little bunch of work. So I said, well, sine is equal to cosine. Let's try squaring both of these. Sine of x is equal to cosine squared of sine squared of x equals cosine squared. Well, I can change sine squared to 1 minus cosine squared from my identities. So that tells me that 1 is equal to cosine squared x plus cosine squared of 2 cosine squared x. Or cosine squared x is equal to 1/2, which tells me cosine of x is equal to positive or negative square root of 2 over 2. And that happens at pi over 4 and 5 pi. So that one, I kind of took a simple problem and made it hard. So. All right, let's take a look at another tricky one here. Solve sine squared of x equals 3 cosine squared x in that interval. Well, again, I did all the problems. Let's convert everything as cosine by taking sine squared and using my Pythagorean identity and calling that 1 minus cosine squared. Well, now I can add this cosine squared to this side and it becomes 4 cosine squared. So I've got 1 is equal to 4 cosine squared, or 1/4 is equal to cosine squared, or cosine of x, taking the square root of that, is equal to positive or negative 1/2. Where does that happen? It happens, happens up here at pi over 3. It's equal to negative 1/2 or positive 1/2 at 2 pi over 3, negative 1/2 at 4 pi over 3, and positive 1/2 at 5 pi over 3. So those are my 4 answers on this one. So you'll notice that sometimes these have 0 answers. They might have 1 answer. They might have 2 answers. They might have 3 answers. They might have 4 answers. So you got to be a little bit careful and not just say, not just assume it's got 1 or 2 answers. All right, so let's take a look at 5 through 8 here. Zoom out a little bit so we can see the whole thing there. It's gonna get cut off at the bottom here, but find all solutions of secant squared x on the interval 0 to 2 pi. Secant squared x minus secant x equals 2. Well, I'm going to write this as a polynomial, like secant squared x minus 2 is equal to 0, and then factor it. secant x minus 2 times secant x plus 1 is equal to 0. So now I've got two solutions. Secant x equals 0 equals 2, or secant x equals -1. Well, if secant x equals 2, that means cosine of x is the reciprocal 1/2. Where does that happen? At pi over 3 and 5 pi over 3. Okay, so hopefully you're starting to learn your unit circles, okay? Because we're going to be doing this a lot. On this side, secant x equals -1. The reciprocal of -1 is just -1. So cosine of x equals -1 at pi over here. So my answer is pi over 3, 5 pi over 3, and pi. Take a look at number 6. I've got 2 sine of x minus cosecant of x is equal to 0. Well, cosecant of x is the reciprocal 1 over sine. Now I've got 0 on this side, and I want to multiply both sides by sine to get rid of that denominator sign there. 0 times sine on the right side is just 0. Sine times 2 sine is 2 sine squared x. And then this reduces nicely just to 1. So this, doing a little bit of math, sine squared x equals 1/2. Sine of x is equal to plus or minus the square root of 1/2, which is plus or minus root 2 over 2. In the interval 0 to 2 pi, where sine equal to root 2 over 2, or negative root 2 over 2, pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. So 4 answers for that one. There's 3 answers for number 5. All right, let's take a look at 7 and 8. I think these are at the top of this here. So I've got 2 secant squared x plus tangent squared x minus 3. I don't know how to reduce this other than let's just convert everything to sines and cosines. So I've got 2 times 1 over cosine squared plus sine squared over cosine squared minus 3 equals 0. Well, to get rid of that denominator, let's multiply both sides by cosine squared. On this side, 0 times cosine squared is still 0. So I've got 2, get rid of the denominator, plus sine squared minus 3 times cosine squared. Now to get rid of that sine squared, I'm going to use one of my Pythagorean identities, 1 minus cosine squared x. So now everything's in terms of cosine. I've got 2 plus 1 is equal to 3, minus cosine squared minus 3 cosine squared is equal to -4 cosine squared x. So that tells me that cosine squared x is equal to 3/4. And cosine x then is equal to the plus or minus the square root of 3/4, which is square root of 3 over 2. Where does that happen? Pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. So keep your unit circles handy. This is just like the one we just did, except it's sine x minus 2 is equal to cosine x minus 2. That happens at pi over 4 and 5 pi over 4. Okay. The one previous to that one. All right. So you can get that from that slide is on the Moodle page if you need it. But we need to finish up here. All right. Functions involving multiple angles. Now this, I don't think there's any like this on the website. I might be wrong, but I don't think I put any like this on the website. If you have a constant, okay, like sine of some constant times u, or cosine of some constant. Then when you get to the end, you have to divide your result by that constant. So what I'm saying is do the whole problem, and your very last step is get rid of that constant. So let me show you an example. So if I have something like this, 2 cosine of 3t minus 1 is equal to 0. Well, I can rewrite this as 3 cosine of 3t equals 1, cosine of 3t equals 1/2. So where is cosine equal to 1/2? Well, that happens at pi over 3 and down here at 5 pi over 3. So those are my two places where 3t is equal to that. We're not done yet. The last step. So my two possible answers are 3t is equal to pi over 3 plus n2 pi, and 3t is equal to 5 pi over 3 plus n2 pi. My last step then is I have to divide by 3 to get rid of that 3. So my final answer is pi over 9 plus n pi 2 divided by 3. And 5 pi over 3 divided by 3 is 5 pi over 9 plus n2 pi divided by 3. And that is what t is equal to. So that's a little bit tricky. Again, I don't think I did anything on the website. If I did, I apologize. Okay. All right, let's take a look at another example here. Three tangent of x over 2 plus 3 equals 0. Well, I could rewrite this as 3 tangent of x over 2 is negative 3, divide through by 3, and I've got tangent of x over 2 is equal to negative 1. Well, tangent is equal to negative 1 here in quadrants 2 and 4. So here and down here, this is 3 pi over 4, because I've got negative square root of 2 over 2, square root of 2 over 2. So divide those and you get negative 1. So at 3 pi over 4, and then since it's tangent, it's always going to be across the circle. So plus n pi. Now to get rid of this 1/2, I have to multiply by 2 now. Multiply through by 2, x is equal to 3 pi over 2 plus 2 pi n. And that's my final solution there. So a little bit tricky. All right, I did want to finish up with 9 through 12 over here. So let's take a look at this one here. I've got cosine of 2x equals 1/2. That says that 2x is equal to either pi over 3 or 5 pi over 3, because that's where cosine is equal to 1/2. That's where 2x is equal, plus any number of iterations around the circle, plus n2 pi. But now to get rid of that 2, I have to divide all of these by 2. So it's pi over 3 divided by 2, 5 pi over 3 divided by 2, plus n2 pi divided by 2. My final answer is pi over 6 plus n pi, and 5 pi over 6 plus n pi, dividing that through. Number 10, tangent of 3x equals 1. Well, tangent of x is equal to 1 at pi over 4 and 5 pi over 4, or pi over 4 plus n pi. The last step, I'm going to need to get rid of that 3, so I'm going to divide both sides by 3. X is equal to pi over 12 plus n pi divided by 3. All right. Finally, number 11 and 12. Cosine of x over 2 is equal to square root of 2 over 2. Well, that means that cosine is equal to square root of 2 over 2 in quadrants 1 and 4, pi over 4 and 5 pi over 4. So don't know where my pointer is. Oh, there it is. So pi over 4 and 5 pi over 4 plus any number times around the circle plus n pi. I need to multiply by 2 to get rid of that 1/2. So it turns out to be pi over 2 plus 5 pi over 2 plus n 4 pi. And finally, number 12, tangent squared of 3x equals 3. That tells me that tangent is equal to the plus or minus the square root of 3. That happens at pi over 3 and 2 pi over 3. And across the circle from each of those. Now I need to divide that by each of those by 3. So pi over 3 divided by 3 is pi over 9 plus n pi divided by 3. And 2 pi over 3 divided by 3 is 2 pi over 9 plus n pi divided by 3. So I just wanted to go over those in the in-class worksheet. Again, I don't think there's one on the website like that. If there is, I apologize. You can ask questions about that. These are a little bit tricky, but I did want to cover the material. All right, so complete the in-class worksheet. Take a look at the website. And again, it's not due till I think Tuesday, so let me know. All right, and that's where we're gonna stop for today.
Are you updating the?
Yeah, I'm gonna do that right now.